everyone. Thanks for the organizer to give me the chance to talk here. I'm very happy to share my work about geometrically finite lists in negative pinch Hadamard manifold in this talk. There are two videos in this session. The first video, I'm going to cover some background, review the definition for geometrically finite lists and what is the known result. And in the second video, I'll just concentrate on one particular result and its proof. So during the whole talk, I'm going to let X denote the simply connected complete Riemannian manifold with the sectional curvature. I denote by K is bounded below by minus kappa square, which is a non-positive number, and also upper bound is -1. If you don't like this this notation, you really can replace this x by Hn, the n-dimensional hyperbolic space whose sectional curvature is always -1. It does not harm for any result. So you can just replace this x by Hn if you feel more comfortable with the higher dimensional hyperbolic space, even just to replace it by H2. Like the story for Hn, or is H2 in the upper half space model, we just can make X diffeomorphic to Rn, where n is the dimension for X. And like for the H2, we can compactify the upper half space by the boundary, which is the S1. It is the union for the point at infinity and this X-axis. So for the negative pinch Hadamard manifold X, we can also compactify it by some visual boundary, which I denoted by the boundary infinity of X. So this is called the visual boundary. It is always homeomorphic to Sn-1, where n is the dimension of X. So after I take the union of X and the visual boundary, I denote it by X bar, and it's a compact set. It's homeomorphic to Bn. The themes we're interested is about the geometrically finite list in for the negative pinch Hadamard manifold. What does that mean? So the geometrically finite list is a property for a discrete subgroup inside the isometry group of X. We usually denote gamma as the discrete isometry subgroup in the whole talk. And in that way, gamma will act on X isometrically. And the discreteness here means like gamma acts on S properly discontinuously. Meaning like for any compact subset K, you can just consider the elements gamma in this group such that gamma K intersect with K is non-empty. So we consider this subset and we find like this subset is always finite, then we say the group gamma acts on S properly discontinuously. As we see, like gamma is a discrete group. So whenever you fix a point P inside our manifold X, you can see like there's a bunch of orbits, which is gamma P. It is the set of or image of this isometry gamma of the points P. So the group is discrete, so it does not have any accumulation inside X. However, when we compactify the manifold, we have X bar, which is X union the boundary. It is a compact manifold because it's homeomorphic to Bn. So we could expect there's some accumulation points for this set in the ideal boundary, which actually we called it the limit set. We denoted by lambda gamma. So this is the accumulation set of the orbits in ideal boundary. Not like the definition is well defined, because if you just pick other point P prime, seems the group gamma is an isometry group. So it really does not matter like if you apply gamma P here and a gamma P prime there, the distance between these two points, these two pair of points are the same because gamma is an isometry. So the definition is well defined independent of the choice of P, which we begin with. The limit set is a closed subset in the ideal boundary, and usually it could be very complicated. For example, if we consider the isometry group gamma in isome of H2, it's well known like isome of H2 is PSL2R. So a discrete group subgroup inside it, we can simply take the discrete group PSL2Z, and the limit set for this lattice, actually it's a lattice. For this discrete group, it's just the whole boundary S1. And it could also be very simple, like it could be just one point like infinity or 0 infinity. In general, it could be very complicated. In general, it's kind of have the fractal shape. Now we can just start to review the definition for geometrically finite list. If we have a discrete group gamma, which is a subgroup of orientation preserving isome of the negative hinged Hadamard manifold X, we say it's geometrically finite if there exists a constant delta greater than 0, such that if we take the delta neighborhood for the whole of the convex set under the group action gamma, the value of this quotient is finite, then we say the group is geometrically finite. Here, let's just briefly recall what this notation means. How of the limit set is the smallest convex closed subset in the manifold. When you consider the closure in X bar is accumulation set is exactly lambda gamma. Then that's what we define for the convex hull of the limit set. So we have gamma X on X, and this hull of the limit set is a closed convex subset inside X. Oops, sorry. Yeah, and then this gamma also acts on the convex hull. And then we take the delta neighborhood for this convex hull and do the quotient. Then we can just say if the volume is finite, then we say it's geometrically finite. That's one definition for geometric finite list. If we forget about the parabolic elements, well, if you're familiar with the definition for parabolic element, that's fine. If you're not familiar with, you can just simply replace the parabolic elements as a translation by 1 unit. So here, if we forget about the parabolic isometries in our group gamma, then we can just give a cleaner and a better and a neater way to say geometrically finiteness. And actually, this is equivalent to say it's convex co-compact. A definition saying like, now we just take the convex hull for the limit set and take the quotient under the group action gamma. If this quotient is compact, then say gamma is convex co-compact, which is also geometrically finite list, because if the group does not have the parabolic element, then geometrically finite list is the same as convex co-compact. There are many different ways to define the geometrically finite list. There are many like equivalent definitions. Some of them are saying the group action inside the manifold. Some of them are just saying the accumulation points at the boundary. So this talk will concentrate 2 of the definition. One is the one we just give by saying the volume of the neighborhood of the convex hull under the quotient is finite. Another definition we'll see actually is to see the orbits of the accumulation points, a classification of points in the limit set. So this is another way to describe the geometrically finite list. We see it from the limit set lambda gamma. In order to review this definition, we need to classify what kind of points in the limit set. For example, if we have a point eta in the limit set, we say it's a conical limit point. If for every point X inside our manifold and every geodesic ray L, which approaches to that point eta we begin with, if there exists a constant A greater than 0, such that the intersection for the orbit of this point X intersect with the A neighborhood for the ray L accumulates to eta, then we say eta is a conical limit point. It might be just a little hard to understand it in the words, but it is very easy to illustrate the picture by drawing what is going on of the orbit. For example, I just pick this point as X. Let me say our eta is infinity. Let me choose the ray as this ray L. As we can see, like if the group gamma is just a cyclic group generated by this scalar, z goes to 2z. So remember, this is just the H2. So it's like the plane model. You can regard every point as the complex number z. So if my gamma is just the cyclic group generated by this dilation, multiplication by 2, then the orbit is, this is x, this is like 2x, etc. So this is the orbit. The orbit will always lies inside L. And we can see like the orbit for this x intersects an AL. No matter how big this A is, you can see like it's always accumulates to the point infinity. So that's why if the group it look like this one, then the point infinity is actually a conical limit point. However, if you consider your group as a cyclic group generated by the translation, which is a parabolic element, then you see like your orbit of this point will be totally inside the horizontal line. And you see, like, no matter how large your L is, this A neighborhood of this L intersect this your orbit is always finite. So it cannot accumulate to the point at infinity. That's why if you take this group as the parabolic element, it won't be a conical limit point. In general, there is a conclusion saying parabolic fixed point cannot be conical. This leads to the next definition for geometrically finite list. It is first of all given by Burden and Moskit in the 3-dimensional, and then Bishop generalized this a little bit in 3-dimensional. And Bowditch later generalized this definition in higher dimensional hyperbolic manifold and even in negative pinched Hadamard manifold. It's the joint work with Karpovich. We also generalized this definition by requiring bounded parabolic fixed point of replace this by parabolic fixed point. So this also, you can regard it as theorem, but you can also regard it as equivalent definition for geometrically finite list. It says that a discrete group gamma, which is a subgroup of orientation preserving isometry of the negative pinched Hadamard manifold X, we say it's geometrically finite if and only if the limit set consists of 2 parts. One part is the conical limit point, and the rest of the point is parabolic fixed point. Remember, like in a discrete group gamma, parabolic elements are countable. So parabolic fixed points are also countable. That's one way to characterize geometrically finite in terms of the boundary, in terms of the limit set at the boundary. So this leads to the second part of this video. The second part says, like, what if gamma is not geometrically finite? Can we characterize that? Can we say some property about the group? If the group is not geometrically finite, we usually call it geometrically infinite. So usually a quick answer to this question is, by definition, we know the convex hull of the limit set under the group action gamma, this quotient, is not compact. This is just by definition if we forget about the parabolic elements for simplicity. However, we want to say more. We want to describe this property more rigorously. So with the joint work of Karpovich, we prove like if gamma is a discrete isometry group of X, and if this group is geometrically infinite, then we say there exists a sequence of closed geodesic lambda I, which is inside the quotient manifold, and it escapes every compact subset of M. What does that mean? So this is the quotient manifold X. Is the quotient of X by the group action gamma. And all this talk, I assume gamma is torsion free, so you don't need to worry about the quotient orbifold. You just consider the quotient as a manifold. And then what we said in this theory is like we can find a closed geodesic lambda 1, lambda 2, lambda 3, etc., which goes to infinity. In the sense, like every time you pick a compact subset K, the number of lambda I intersect K is non-empty. This kind of number is finite. So each time you have a compact set K, you have only finite many closed geodesic in the sequence, which is contained inside the compact set, and there are infinite many which is outside of the compact set. So this is what the result is saying. Note that in the 3-dimensional, this is a very important theorem proved by Bonneholm, and it actually gives a characterization for the geometrically infinite ends of finite generated 3-dimensional manifold. And even more, I think in 3-dimensional, Bonneholm can prove more, and he actually can prove like there exists the escaping geodesic whose length is bounded. Though here, when we generalize this result to higher dimensional or even negative pinched Hadamard manifold, we're just saying there exists the escaping geodesic. We don't have any other information saying what is the length, or whether the length can go to infinity, or whether the length is bounded. But in the second video, with additional assumption, we can say more about this escaping geodesic. So one corollary about this result is if we have this gamma is a geometrically finite group, then yes, then we can describe the limit set lambda gamma as two parts, as we see for geometrically finite case. One part is this conical limit point, and the rest of them are non-conical limit points. Just recall, like if the group is geometrically finite, then this set consists of parabolic fixed point. It is countable. But if the group is geometrically infinite, then this set has the cardinality of continuum. So it is more than parabolic fixed points. How do we see that? So so the proof actually is very simple. Let's just briefly talk about the idea of the proof. So we have a sequence of escaping geodesic here denoted by lambda 1, lambda 2, and lambda 3, etc. And I have just the point x. I just fix any point x inside my manifold. And I choose the shortest geodesic between x to the closest geodesic lambda 1, denoted by mu 0. And for lambda 1, lambda 2, let me choose the shortest geodesic mu 1 between these two closest geodesic, and etc. mu 2, mu 3. Now I'm going to construct a path. The path is constructed in this following way. I starting from x, travel along mu 0, and travel along lambda 1 from this intersection point, x1 minus to x1 plus, going back here, and travel along mu 1, and keep going like this way. So this will give me a path from x to the end point of this infinite path. And this is not the only way to construct the path, because whenever each time you touch lambda 1, you have different choice to make the path, right? For example, when I reach here, I can just go directly to x1 plus. However, I can also wrap it one time and then stop here and travel to mu 1. Even more generally, I can just wrap around as many times as I wish and then stop here to travel along mu 1. So at each closed geodesic, lambda 1, lambda 2, lambda 3, you have infinite many choice, like how many times you want to wrap around the closed geodesic. So each time you get a different path. There is a questions like, what can we say about the endpoint of this path? So first of all, the claim is like the endpoint of this path, each path is a non-conical limit point. It lives here. It cannot be conical. And then you might just ask yourself, like, for any two different paths, do they have the different endpoints? Because there are uncountable many paths by this construction, right? Because at every stage you have uncountable many, you have like infinite many choice. So we have uncountable many paths. If any two different paths has different endpoint, then we can get at least the cardinality for this set has the continuum, like the candle set. And it is true, like for every different path, you have different endpoints. The way we see that is we want to leave the path in the universal cover and see how it looks like. So this is inside the quotient manifold. When I lift to the universal cover, I lift it to x, and this x, once I fix a lift as x tilde, then I can just find a conical lift for lambda 1, which is a1, lambda 2, a2, lambda 3, a3 here. So the path which I travel from x and go directly here will correspond to the path of x tilde, and then travel along part of a1, and then go to next one, and it goes to a2 and travels along the lift of mu 2 tilde. That's one thing. And if you just wrap around lambda 1 several times, like here, like this, wrap around several times, what did you see in the universal cover? You still start from x tilde, but now this time you travel along mu 0 tilde, which is the lift for mu 0. But you don't stop here. Instead, you just travel more and you stop at some lift of x1 minus tilde here, and then you should go somewhere of the image of a2 tilde, which projects to the closer geodesic lambda 2. So for different paths, you can see like you can concatenate these two different paths here, and then you get bi-infinite paths. The key point here is like this bi-infinite piecewise geodesic path is a uniform quasi-geodesic, so it must have different endpoints. That's the idea for the proof. So after we see the limit set for the characterization for geometrically finite group or geometrically infinite group, that naturally leads to part 3 of this video. What can we ask about this limit set, lambda, the whole limit set, or the conical one, non-conical one? Since they can have very irregular shape, they could have like the fractal. So the measure question we ask here is actually ask the Hausdorff dimension for this set. It's a finer measure than the Lebesgue measure. Why we care about this Hausdorff dimension for these three sets, and because it's like there are some recent results like telling us like if we know the Hausdorff dimension, it actually can tell us a lot of information about the group, algebraic information or geometric information. For example, there's a theorem of Panka and Suto. They prove like if gamma is an isometry group of Hn, let's assume it's torsion-free, discrete, and non-elementary. Non-elementary means the limit set has more than 2 points. Another assumption is like if we know like the Hausdorff dimension for the whole limit set is smaller than 1, then surprisingly we actually know the group is a free group. That tells us some algebraic information about the group. And then a theorem of Kulkarni says like if gamma is finitely generated, note this is a additional assumption. And if we know the Hausdorff dimension is smaller than 1, then we can conclude like gamma is geometrically finite. That's like tells you some geometry information for the group gamma acting on the space. That's the story for the whole limit set. What about the Hausdorff dimension for the conical limit point? For the conical limit points, actually, it has a deep theory or the deep dynamics theory called the Patterson-Sullivan's measure. By the work of Sullivan and Bishop and Jones, we know like whenever you have this discrete group of the negative pinch Hadamard manifold X, saying it is non-elementary, then every time you see the Hausdorff dimension for this conical limit point, it is always equals to an invariant of this group, which is called the delta gamma critical exponent. The critical exponent of a group is defined in terms of the orbit. So you just pick one point P inside your manifold X, and you take the radius orbit of this centered with the point P. And there are like some points in the orbit gamma P will live inside this radius orbit. So we just take the intersection for this orbit and the radius r ball and see the number of this orbit inside the ball, do the ratio with r, and take the limit when r goes to infinity. That's how we define the critical exponent delta gamma. So it is a group invariant. In the same like if you have a group gamma and a group gamma prime, they're quasi-isometric to each other in terms of the Cayley graph, if both of the group are finite generated. Then the delta gamma is an invariant for that group. So for the Hausdorff dimension for the conical limit point is always equals to this critical exponent and is smaller or equals to n-1. That relates to the deep theory in dynamics about the Patterson-Sullivan's measure. So what can we say about this non-conical limit point? In terms of like very less is known about this non-conical limit point. It's a very mysterious subset. We only know like the Hausdorff dimension for this non-conical limit part is smaller or equals to the Hausdorff dimension for the whole limit set, which is smaller or equals to n-1 because the boundary is n-1 dimensional sphere. And we just know like it's greater or equals to 0. So we're asking whether there are some examples you can reach the upper bound n-1, or whether there are some examples, you can reach the lower bound of 0. If the group gamma is geometrically finite, we know this set consists of parabolic fixed point, which is countable, so it's always 0. So in order to study the Hausdorff dimension for non-conical limit point, it actually only makes sense when the group is geometrically infinite. So first of all, the theorem of Valence and Milan prove like if gamma is an isometry group of the two-dimensional hyperbolic plane, geometrically infinite, and also you assume the whole limit set is the whole boundary S1, then you can prove like the Hausdorff dimension for the non-conical limit part is 1, which is exactly the same as the Hausdorff dimension for the whole limit set. So you can see like this is the upper bound because this is n equals to 1, n equals to 2. So that gives you some examples where the upper bound will be reached and the Hausdorff dimension for the non-conical limit point is the same as the conical one. With joint work with Kapovich, we also find an example gamma, which is geometrically infinite inside the isome of H2, such that the Hausdorff dimension for the limit set is 0. So this lower bound can also be reached, and actually the gap between this Hausdorff dimension and the whole limit set can be arbitrarily large. So in the second video of this series, we'll concentrate on the question asked by Karpovich, saying like, is every finite generated Kleinian group gamma inside isom of HM with this critical exponent smaller than 1 geometrically finite, or whether it is virtually free? Thank you. Thank you very much for everyone's listening.